right, welcome back, folks. We are now beginning Unit 2. We have finished everything to do with cardiovascular, and we are now going to move into respiratory. But all of that material that we've learned so far is still going to come back multiple times throughout the semester. So make sure to keep those notes handy. Make sure to still clear up anything that you might be unsure about from the previous chapters, because all of that material, we will build on it. It's expected that once we get to this point, you understand all of that material. So if there's anything that you don't, please let me know, and please let's get it cleared up. Let's begin with our not really attendance questions. What is olfaction? Oropharynx is primarily which tissue? What is the significance of the C shape of the tracheal rings? And what is pleurisy? And you should pause the video and try to answer these on your own before we go over them. And these are coming from that part of the chapter that is self-study. What I did here, because there's so much physiology the rest of the semester, the anatomy portions of each chapter are primarily going to be self-study. So this is everything from section 22.1, which is all of the anatomy of the respiratory system. First, what is olfaction? Olfaction is just your sense of smell, and your sense of smell is kind of a big relationship between your respiratory system and the sensory part of your nervous system. Next, the oropharynx is primarily which tissue? Well, first let's start with just pharynx. The pharynx is the shared cavity at the back of your nose and mouth. And for the most part, this is the area where both air and food pass. At the bottom of the pharynx, it actually separates into the air passageway, so the larynx and the trachea, and then also the food passageway, the esophagus. But the pharynx is divided into three separate spots: the nasopharynx, the oropharynx, and the laryngopharynx. So the nasopharynx is just the back of the nose. And since normally the only thing that should be passing through that area is air, it's lined with pseudostratified columnar epithelium. But once we get to the mouth, the back of the mouth is the oropharynx, and just below that is the laryngopharynx. And in both of those areas, food and air both are passing through, so there's a lot of friction in that area. And the oropharynx and the laryngopharynx both are primarily lined with the stratified squamous epithelium. Remember that from Bio 137. Next, what is the significance of the C shape of the tracheal rings? Now, if we were to look down, if we were to have someone whose head had been removed, and we were to look down into their neck and see their larynx, well, the larynx has some cartilage rings, and those cartilage rings are basically C-shaped. They're shaped like that. And the function of this cartilage is to give support. Now, really, a ring of cartilage would give better support. That way you've got support on all sides, but that's not what we see. There's an open space right here where we do not see any cartilage. It's just smooth muscle right there. What's the significance of having a C shape versus that complete circle? Well, that's because if we were to be looking down at someone, this way would be the front. So back here, where the open space is the back. And just behind the trachea is where we see the esophagus. And every time that we swallow a bolus of food, the esophagus actually has to expand to allow that bolus of food to pass through. And if we had a complete ring of cartilage, the esophagus would be unable to expand. So by having a little bit of open space in the back, it actually allows the esophagus to expand into the trachea a little bit without resistance. Next, what is pleurisy? Pleurisy may have been covered in Bio 137 with you. Remember in the all of the ventral body cavities, like the thoracic cavity, which contained the pleural cavity, the mediastinum, which contained the pericardial cavity, and then the abdominopelvic cavity, all of the organs there had that two-layer membrane. It's actually a single-layer membrane that's folded back on itself to produce two layers. And those membranes surrounded all of those organs. And those membranes, which are called serous membranes, are given specific names depending on which organ they surround. So if we were to look at the lungs, well, the lungs have that membrane surrounding them also. So I'm going to draw that as kind of a dotted line. And those membranes, like I said, they fold back on themselves to create basically a two-layer membrane. And in between those two, there is this fluid called serous fluid. And that serous fluid acts as a lubricant. Around the lungs, those membranes are called the pleura. That fluid is called pleural fluid. Every time you inhale and your lungs get enlarged, and then every time you exhale and your lungs get smaller, well, those two membranes rub against each other. And the lubricant, in this case the pleural fluid, acts as a lubricant to keep those two layers from irritating each other. Well, pleurisy is a disorder that results from not enough of that serous pleural fluid. And if you don't have enough of that fluid, those two layers irritate each other. And every time you take a breath, there's this crushing pain in your chest, and it can feel a lot like a heart attack. And as a matter of fact, a lot of patients that show up in the emergency room thinking they're having a heart attack are actually experiencing pleurisy. So before we get rolling, coming up, we're going to be covering the immune system. But the immune system is in a chapter that contains both lymphatic and immune. The first portion of the chapter is lymphatic, and remember, it is self-study. And I strongly encourage you to do that lymphatic, the reading, which has assigned reading and connect questions with it. I strongly encourage you to do that before listening to the immune system lectures, because the immune system lectures are going to refer to things that you learn in the lymphatic system. Now, the lymphatic system is, most students think it is the easiest material all semester, so it's okay that it's self-study. There's not any real physiology that goes along with it. It's mostly anatomy and just some of the introduction of what the functions of the lymphatic system are. So it's not very difficult material at all, and it will better prepare you for the immune system lectures. Now, in the self-study part of respiratory, there actually was a thinking cap question if you saw those asterisks. So let's go ahead and go over what that thinking cap question was. And this is, people with sinus problems often develop ear infections soon after. And really the opposite's true also. Some people with ear infections will develop sinus infections soon after. Why is that? And try to answer this on your own. But the reason that is in your ears, on the other side of your eardrum, there is a tube that goes down and it actually connects your ear cavity to your nasal cavity. in the back of your nasal cavity, there's a small opening on each wall, and that goes up into the ears. That's called the eustachian tube or the auditory tube. Now, the eustachian tube, the auditory tube, is there to equalize pressure between the inner ear and the atmosphere. And sometimes when that pressure isn't equalized, you have this stuffy feeling in your ear. Sometimes that eustachian tube will actually squeeze shut. And if you yawn or chew gum, sometimes you get this popping feeling. And that's that eustachian tube opening up and then the pressure equalizing. But because of that connection between the back of the nose and the inner ear, if you were to get an infection, that's a really easy pathway for those bacteria to be transferred from one location to the other. So a lot of time people with sinus infections will often develop ear infections not long after that. So let's move on to the actual meat of this chapter and introduce some terms. We're going to talk about just basic terminology in this lecture, and we're also going to introduce a little bit of neural mechanisms for breathing, and this is all going to kind of lay the foundation for the next couple of lectures. So pulmonary ventilation, that's really just another term for breathing. Pulmonary ventilation is just moving air in and out of your lungs. And then there's two steps to pulmonary ventilation. There's inspiration, which is inhaling, breathing in, bringing air into your lungs. And there's expiration, which is exhaling, breathing out, moving air out of your lungs. And there's different types of breathing. There's something called quiet breathing or eupnea. Quiet respiration, normal quiet breathing. This is just when you're sitting around and you're not doing anything to exert yourself. You're just sitting there, not really paying attention to your breathing, and it just happens completely on its own without any, conscious input. But then there's forced respiration. And forced respiration is what occurs when you are intentionally moving air, such as when you're blowing out a candle, blowing up a balloon, if you play a wind instrument, if you sing and you're trying to project your voice. Now, just like we saw with the medulla oblongata and the cardiovascular centers that were there, we saw, the cardioacceleratory, cardioinhibitory, and also the vasomotor centers. The medulla oblongata, remember, is a part of your brain that keeps you going without you really having to think about it. It controls a lot of those things that keep you alive without your conscious input. And just like those centers that we've already talked about, there are some respiratory centers in your medulla oblongata. And these are the DRG and the VRG. Now this picture is on page 860 of your textbook. And right down here is the medulla oblongata. And this is where we find the DRG and the VRG. Now the VRG, or the ventral respiratory group, is just in front of the DRG, the dorsal respiratory group. The VRG, the ventral respiratory group, is responsible for setting your respiratory rhythm. It sets your respiration rate. And it does that by initiating inspiration and initiating expiration. And it does this kind of automatically. You remember how when we were looking at the SA node of the heart, that it completely depolarized on its own at a regular rate without any input? Well, the VRG does the same thing. it spontaneously depolarizes at a regular rate without any input. So it causes you to inhale and it causes you to exhale. But right behind that, there is the dorsal respiratory group, the DRG. And the dorsal respiratory group modifies the rate set by the VRG, the ventral respiratory group. The dorsal respiratory group modifies the rate set by the ventral respiratory group. Essentially, it tells it to speed up to depolarize more quickly, or it tells it to slow down to depolarize more slowly. Remember how when we were talking about the SA node, it could be sped up or slowed down? The VRG can also be sped up or slowed down, and it's done by the DRG. So I like to tell my students, think about the VRG, the ventral respiratory group, as the autopilot. The DRG, the dorsal respiratory group, is kind of like the backseat driver. Speed up, you're not going fast enough, or slow down, you're going too fast. That's what the DRG does. But just above the medulla oblongata is the pons. And the pons also has a respiratory center called the pontine respiratory group, the PRG. And the pontine respiratory group has a few jobs. First, it smooths the transition between an inhale and an exhale. Most of the time, we don't pay attention to our breathing. And if we do pay attention to our breathing, it's really hard not to influence how we're breathing. But if you can just let yourself breathe and pay attention, when you inhale, you don't breathe in and then have this pause and then you breathe out. No, you're breathing in and then you're breathing out. It doesn't go breathe in, pause, breathe out. No, it's you're breathing in and then you're breathing out. It's a very smooth transition. And the pontine respiratory group is responsible for that. But also, the pontine respiratory group times your breathing based on certain activities. So, if you're giving a speech, you don't stop in the middle of a word to take a breath. No, you almost without thinking about it, take a breath at the end of the sentence when there's a natural pause there. When you're singing, you're breathing in very specific spots. Things like that are under the control of the pontine respiratory group. So the PRG can still give input to the VRG. And, in a manner of speaking, it also gives input to the DRG. Now, as a general rule, in my class, I do not have anyone learn numbers. Back when we were talking about the heart, I did not have anyone learn the numbers as far as what were the numbers involved with depolarization, repolarization, action potentials, things like that. But in the respiratory system, there are some numbers that you need to know. And the first is atmospheric pressure at sea level. Atmospheric pressure at sea level is a pressure, and you do need to know this number. And just like every pressure that we've talked about, the pressure is in millimeters of mercury. Now, atmospheric pressure at sea level has a pressure of 760 mmHg. Now, if we went up higher in the mountains, there would be less atmospheric pressure. That would be a lower number. If we went down deep into a valley, then there would be more atmospheric pressure. It would be a bigger number. But we always talk about atmospheric pressure at sea level, and that's what we're going to do in this class. So when I ask you what is atmospheric pressure, assume that we mean at sea level, 760 mmHg, and you do need to know that number. Now, Atmospheric pressure, what is it? If we go outside, it doesn't seem like there's anything above us or around us, but there is. There's all sorts of atmospheric gases, and we'll see what those are in another lecture. But the atmosphere, all of those gases, are constantly pressing down on us. And if we were to go outside with the right instrument, we could measure that it's pressing down on us with a force of 760 mmHg. Now, if we were to go up a really tall mountain, even though we don't see it, there is less atmosphere above us. So there's less pressure against us. That's why it would be a lower number the higher we go. And if we were to go down deep into a valley, there's more atmosphere above us. So there's more above us pressing down against us. It presses with greater force, and that's why the lower you go into a valley, the greater the atmospheric pressure. Another type of pressure we're going to be talking about is the intrapulmonary pressure. The intrapulmonary pressure is the pressure inside of our lungs, inside of our alveoli, those little air sacs in our lungs. And the intrapulmonary pressure rises and falls with every inhale and exhale. When we inhale, we're bringing more air in, so the pressure goes up. When we exhale, we're pushing air out, so that pressure goes down. But even though it's rising and falling with each breath, at the end of every inhale, and again at the end of every exhale, intrapulmonary pressure is equal to atmospheric pressure. Now, that may not seem logical since it's constantly rising and falling, but in the next lecture, we're going to see how that is. Just know intrapulmonary pressure rises and falls with each breath. And at the end of every inhale, and again at the end of every exhale, it's equal to atmospheric pressure. Next, the intrapleural pressure. Intrapleural pressure is the area inside of our chest, but outside of our lungs. Inside of our chest, but outside of our lungs. Now, this is always a little bit less than intrapulmonary pressure. It's about 4 less than intrapulmonary pressure. So, if atmospheric pressure is 760 mmHg, and if intrapulmonary pressure at the end of an inhale or at the end of an exhale is equal to atmospheric pressure, then it is also 760. Then what would intrapleural pressure be at that same time? It would be about 756 mmHg. Now, that number can be a little bit greater or a little bit less, but it's always about 4 less than intrapulmonary. And that's because of some special features that the lungs have. The lungs are kind of like big rubber bands or balloons. They have recoil, they have elasticity. When they are stretched, they snap back on their own. They have recoil. So they're constantly trying to snap back to that smaller size. Also, the lungs are moist. The lungs have this liquid all around them. And that liquid is mostly water, like everything else in our body. And water has surface tension. That goes way back to chapter 2 in Bio 137. And surface tension is the tendency for water molecules to stick to each other because of hydrogen bonds. Water molecules stick to each other because of hydrogen bonds. And this kind of makes water form a shell around things that are wet. Now, like we mentioned, the alveoli, the little air sacs in your lungs, every time you breathe in, they expand, and every time you breathe out, they shrink back down because of that recoil. But when they shrink back down, those water molecules want to form a shell around that alveolus. And then when we try to breathe in again, that surface tension resists that expansion. Luckily, we have some cells that we learned about in the self-study part called type 2 cells. And the type 2 cells secrete surfactant. And surfactant reduces surface tension. So that when those alveoli shrink down, there's not as much surface tension that develops, and then they can expand again. But there's always a little bit of surface tension there. And that surface tension wants to squeeze the alveoli down, wants to squeeze the lungs down to their smallest size. Now, because of that recoil, that elasticity, and because of the surface tension, the lungs are constantly pulling downward, and that creates a little bit of a vacuum in that cavity. And that's why the intrapleural pressure is always a little less than the intrapulmonary pressure. Now, the transpulmonary pressure isn't so much a pressure itself, it is a difference in the intrapleural and the intrapulmonary. And we find the transpulmonary pressure by taking intrapleural and subtracting intrapulmonary. So normally the transpulmonary pressure is about -4 mmHg. -4 because it's intrapleural minus intrapulmonary. Like I said, there's about 4 difference. But intrapleural is a smaller number, and if we subtract a bigger number, we get a negative. Now, the transpulmonary pressure is what determines the size of the lungs. The greater the magnitude of this number, now, I know this is not a math class, but when I'm talking magnitude, basically that just says ignore the negative sign. -4 and +4 have the same magnitude. -10 and +10 have the same magnitude. So, the magnitude of the transpulmonary pressure determines the size of the lungs. When the transpulmonary pressure has greater magnitude, then it pulls on the lungs more. Let's say if the intrapulmonary pressure, instead of 756, let's say it was 750. Well, what's transpulmonary? At that point, it's -10. So transpulmonary pressure of -4 pulls on the lungs. Transpulmonary pressure of -10 pulls on the lungs harder. If we had a transpulmonary pressure of -2, it would not pull on the lungs as hard. So the greater the magnitude of the transpulmonary pressure, the harder we're pulling on the lungs, and the bigger the lungs will be. All right? If that doesn't make sense, play it back a couple of times, listen to it, try to imagine it. The greater the magnitude of the transpulmonary pressure, the harder we pull on the lungs. Think of the lungs as a rubber band. The harder we pull on them, the bigger they get. Now let's talk about atelectasis and pneumothorax. Those are some crazy words. Now, first let's talk about pneumothorax. Pneumothorax literally just means a hole in the chest. And that's what we see right here. A hole in the chest. Now, if we have a hole in the chest, that allows for a bad situation to develop. So let's think of what this really means. out here where we see this white, this is the atmosphere. What is atmospheric pressure? 760 mmHg. Inside the lungs, the intrapulmonary pressure, what is that? That is also 760 mmHg at the end of an inhale or at the end of an exhale. Now, what is the area inside the chest but outside the lungs? So the intrapleural pressure. It's about 756. So it gives us a transpulmonary pressure of about -4. But let's say something happens, you land on a ski pole or something, and it pokes a hole in your chest that goes all the way through into this intrapleural space. Now there's air that can get into the intrapleural space from the atmosphere. I hate that it shows air coming out. Really, it would be air going in. But what would be the result? Well, this 756 would actually go up to 760. And the transpulmonary pressure would be what? It would be 0. Because intrapleural 760 minus intrapulmonary 760 gives us 0. And what happens if there is 0? Well, we're not pulling on the lungs very much at all. As a matter of fact, we're not pulling on the lungs at all. And then elasticity and surface tension take over. And that's what we see right here. The lung collapses to as small of a size as it can get. And that is called atelectasis. Atelectasis is collapsed lung. Pneumothorax leads to atelectasis. And that's because this atmosphere can get into the intrapleural space. And once that happens, and there's an equalization between atmosphere and the intrapleural pressure, that means there's also equalization between the intrapleural pressure and the intrapulmonary pressure. There's no pulling force to hold the lungs expanded. The lungs shrink down. The lung collapses. And the last thing we will talk about in this lecture is pressure-volume relationship. Now here, I want to point out that just like in Bio 137, in Chapter 2, chemistry was really important. Now, physics is really important. We're going to talk about physics a lot in this chapter. And I know most people hate physics. I didn't like physics much myself. So I'm going to make this as easy as possible. Don't worry just because you hear the word physics. I'm not going to make it hard physics. I'm going to make this as very straightforward as possible. Now, the first thing we're going to learn about physics is something called Boyle's Law. And Boyle's Law is written as P1V1 is equal to P2V2. But really, for our class, that's just a bunch of jargon. Really what it means is pressure 1 times volume 1 is equal to pressure 2 times volume 2. There's a much more important way of writing this that's going to really apply to our class. And that is that pressure and volume are inversely related. Or we could say when there's an increase in volume, there is a decrease in pressure. Or vice versa. When there's a decrease in volume, there's an increase in pressure. When volume goes up, pressure goes down. When volume goes down, pressure goes up. That's going to be the foundation for how we inhale and exhale in our next lecture. But let's look to see why that is. So here on the left, there's a container and it's got a lid. and inside there is some sort of gas. Now, this gas has various molecules represented by these black dots. And we can see over here, there's a certain volume, and those dots are spread out. So there's a certain pressure. But now let's say we have something that pushes down on this lid. And now it looks like it does over here on the right. We've pushed the lid down. So the volume has gotten a lot smaller. And if we look at those black dots, those air molecules, they're now crowded closer together. So the pressure has increased. On the left, we had a high pressure. On the left we had a high volume and a low pressure. And on the right, the volume went down, but the pressure went up. If we were to raise the lid back up, then the volume would go up while the pressure goes down. So whatever happens to the volume, the opposite happens to the pressure. But this sets up something very, very similar to what we saw in Bio 137 with diffusion based on concentration. So let's see what happens. Now let's say instead of having instead of having one single container with two separate pressures and volumes, let's say we now have two containers. This is not the same container that we're looking at two different points in time. These are two separate containers. On the left, we have a container that's got a large volume and a low pressure. On the right, we've got a container that's got a small volume and a high pressure. Now let's say these two containers are connected by a tube. We connect those two containers together with a tube. And we open that tube up so that those two containers, there's a pathway between them. Well, over here on the right, we've got a high pressure. Over here on the left, we've got a low pressure. When there are two different pressures and there is an available path between them, there will be movement of molecules. I'm going to say that again and try to see if it sounds familiar. When there are two different pressures and an available path between them, there will be movement of molecules. So that should sound similar to diffusion in Bio 137. So to make it sound even more similar, I'm going to say it a little bit different. Things like to move from an area of high pressure to an area of low pressure. Well, that is diffusion. When we looked at diffusion in Bio 137, we said things will move from an area of high concentration to an area of low concentration. But diffusion works with pressure also. And it's the exact same concept. Things will move, things will diffuse from an area of high pressure towards an area of low pressure. So if we had this setup like I've got drawn here, some of these air molecules would diffuse from the right side to the left side, from high pressure to low pressure. But how long would that diffusion last? Just like we saw with concentration, we will have diffusion until equilibrium occurs. Molecules will move from the right side to the left side until those two pressures are equal to each other. Molecules will move from the right side to the left side until those two pressures are equal to each other. Okay, make sure that that makes sense before watching the second lecture, because the second lecture is going to take this and apply it to show how we breathe. All right, I hope everyone's doing well, and I will talk to you next time.